Well, see that? Hi, guys. Let's see, Giovanni and Daphne's here. We've got Zach and Sophia, Matt, Thomas, Ainsley, Ian, Grady, Richard, Connor, Matt Driscoll. I don't see you. Will Lyons, Thomas Boyd, Dylan, William, and Joey. Want to see your face. How's everybody doing? How'd it go for the last week while I was just doing a video? I saw that a lot of people didn't even watch the video. Like I only got like, I think 6 or 7 views, but you guys managed to get your homework done without it? Just curious what you're doing. Are you just looking in the book? Because I know some of you got your homework done.
I went to some math tutors.
Oh, okay. But you didn't watch the video?
I watched I watched the first one.
Okay. Everybody else seemed to be okay with all that. All right. The video is very, very much like the homework though. All right, so I'll obviously, like every day, I'll post this online as well. For those of you that do watch them pretty regularly. Okay, so guys, we're almost near the end. This last section is about integrals, which is kind of an inverse of a derivative. And it's not like a regular calculus course. This is applied calculus. So we're not going to delve too far into integral formulas, because most of the time when you're doing integral calculus, you're using a calculator, and I'm going to show you how to calculate integrals using your calculator. But we only have 3 short sections left: 5.1, 5.2, and 5.3. Then we'll have review for chapters 4 and 5 test, and then we'll have chapter 4 and 5 test. Then we'll have review for the final exam, and then we'll have a final exam. So you are on the downhill slope now. You guys can all make this. I know you can. Okay, so let's see. We're going to do 5.1 and try and get through 5.2. I don't know if I can or not, but I do have on Wiley, as of right now, everything's live, 5.1 and 5.2 at least. I'm not sure I'll get through all the way 5.2. This is not too complicated stuff, so I think you guys should be fine with this. Okay, so in chapter 2, we use the derivative to find the rate of change of a function. Here we see how to go in the other direction. Remember I said earlier that an integral is kind of like the inverse of the derivative, right? So it's kind of how can you undo a rate, right? Because derivative is all about rates, right? So if you look like here, let's see. So you can, like if you think of this right here, we start by finding the distance traveled from its rate of change, the velocity. See how we're kind of going backwards? When we find the derivative, we're finding the rate of change, right? The slope at a particular point. But what if all we know is the rate of change, and we're curious how can we get back to the original function, which is distance, right? So this is this first section uses some basic information to try and get you to see, like, okay, I see distance traveled would be the area under the curve of the original function. And I'm going to get to that for that. So this is kind of a practical example for explaining how the derivative relates to the integral. Okay, so the formula that we're going to use to do estimations is the distance formula, right? Rate times time, or velocity is rate, right? So rate times time. And then later, you will use just your calculator.
See the screen, Professor.
Oh, thank you. I need to share it first, don't I? Thank you. Okay. Now you can see it, yes? Let me make sure I can see all of you guys too. There you go. Okay. Okay, so I think you guys were listening at least. So in chapter 2, we use the derivative to find the rate of change at a particular point on a function, right? And a real practical example of this is thinking about speed and which is velocity, right? Rate of change and distance. So if, let's say, instead of having how far something was, instead we just had a whole bunch of points at what the derivative was, right? In other words, the speed at a bunch of points, but we didn't know how far we traveled. So we can use this formula, distance would equal whatever velocity times time is, right? And later we'll use not really formulas, but more like, well, I guess it is a formula. So this is really just for you guys to understand, but do know that in section 5.2 that there are problems like these examples that I'm going to do for you today. So here, then this practical example, what we're going to do is we're going to see how we're going to estimate the distance when velocity changes. As you know, when you ride your bike, if you're going up a hill, you're going to go slower, right? Your rate of change is slower than when you're going down the hill or whatever. So what we have here is velocity at different points. And what they're saying here is that every 2 seconds, that was the instantaneous speed. Okay, so what we want to do is we want to get back to, oh, those are my cookies. 1 second. You got it? Okay, thanks. I make the best cookies, you guys. It has white chocolate chips and coconut and usually nuts like pecans or something like that. They're just delicious. It's right there, the blue. Thank you, John. Okay. So it says, suppose a car is moving with increasing velocity. Notice that the velocity or the speed at each one of these points is increasing, right? And then we measure the car's velocity every 2 seconds. So you should look for this in the tables in the problems, right? It won't always say, but this is 2 seconds, right? Between each measurement of velocity. Okay, so we measure it every 2 seconds as shown in the table. How far has the car traveled? So what we're going to do with this is we're going to do what we call a lower estimate and an upper estimate. To compute a lower estimate of how far we traveled, we can take these numbers here. Well, I think I'm going to switch back to my other pen. I'm not sure. This one as well. See, this one has a tip like this, and this one has a tip like that. This one tends to work a little better. All right, so this is the lower estimate. So this is what we're going to do. Since we know that velocity times time is distance, right? What we can do is we can make an estimate. So the lower estimate starts with the front numbers, right? So you would say velocity times time. So the velocity at the first interval there is 20. And we're talking about 2 seconds. Okay, so we keep doing this. We can say, all right, we'll use the next value for velocity and say, then it went 30 feet per second for 2 seconds. Then it went 38 feet per second for 2 seconds, and so on, right? Plus 44 for 2 seconds, plus 48 for 2 seconds. And notice because the speed is increasing, a lower estimate of how far this is going to go would be with the lower velocities, right? So if you add all that up, you're going to get 360 feet. So that's a pretty good estimate. That's not bad based on, we just happen to know 1, 2, 3, 4, 5, 6 different velocities, right? Now to find the upper estimate, you're going to use the upper levels here. So you wouldn't start out with the first number. Instead, you're going to start out with 30 here. So this is your upper estimate. And do the same thing. So instead of 20, we're going to start with 30 velocity, but it's still 2 seconds. Then we'll go to 38 for 2 seconds, 44 for 2 seconds. You can see by looking at these numbers why one would be a lower estimate and the other would be an upper estimate, right? And then we've got 48 for 2 seconds, and finally 50. And if you calculate all of that, you would get 420 feet total distance traveled. But an even better estimate would be averaging those two, right? Because the distance traveled is going to be in between the lower estimate of 360 and the upper estimate of 420. So just given that data alone, a better estimate would probably be an average of those two numbers. So obviously we would take 360 and add it to 420 and divide by the number of numbers, right? We're just finding the average. So a better estimate that we could do would be 390 feet. Because we can say it's somewhere in between there, right? So probably a better informational estimate would be the average of those two numbers. Now let's visualize what that looks like on a graph. So a lower estimate, and let me color code this, what I use, pink and green. Okay. A lower estimate here, notice, would be time of 2 and velocity of 20, right? And that's this first number that I did there. And remember, if you have distance equals rate times time, that's a rectangle, right? So here's time and here's your rate. So all of these rectangles represent, and remember, this is the original function, right? So all of these represent an under or lower estimate, right? Notice that it falls underneath the normal curve, right? And then anything above would be your upper estimate. So this whole, and so on. And then what you get is their average is what you get when you compute the average like we did in the last example. So it's important that you understand the rectangles and how they relate, especially for the next section, because then they'll ask you to do your own table based on a graph that they give you, and that will be in the next section. I'm hoping to get to at least that part because it would make more sense if you get it in the same day. Okay, so you guys all understand why these are overestimates. Notice that they're on top, right? The underestimates will always be below the curve. Any questions so far? Is pace okay, guys? You need me to slow down? Thank you, Joey. Thanks, Daphne. Okay. Hey, there's Thomas. I miss seeing my students' face. I really do. So I love when you guys turn your cameras on. Thank you. Okay. Now, what we have here is if you take the number of times that, see back here in our table, we're only estimating the derivative, right? Or the instantaneous speed every 2 seconds, right? So what we end up with is every 2 seconds, we've got a rectangle under the curve. Well, what if we measured more times, right? So here, velocity is being measured every half a second, and here it's being measured every quarter second. So eventually, if you keep making those rectangles smaller and smaller and smaller, and what you're making smaller is how often you're measuring. Come here. Come here. Say hi to Lily, guys. Isn't she cute? She wants a little attention. I've been working all day. Say hi.
What's your dog's name, Mrs. Alderman?
This is Lily. She's a Shiba Inu. Doesn't she look like a husky? Little husky.
She's beautiful.
Face. Oh. All right, let me let her outside. I'm sorry, guys. Sorry, guys. I haven't given her much attention today. Okay, so you can kind of see here, and I should probably write this down. As the velocity is measured at smaller and smaller intervals, then what happens is you get the distance of travel is going to be exactly equal to the area under the full curve. And can you guys imagine that we could make skinnier and skinnier and skinnier intervals until it's almost infinite, right? Which we'll go into next class. So can you guys buy that? Do you buy into the fact that if you make these rectangles skinnier and skinnier and skinnier, infinitely skinnier, that eventually you're going to get this curve? Yeah? Everybody believe that? Okay. All right. Now, in this example, and there's one like this on your, maybe two, like this on your Wiley homework. If we buy into the fact that the distance traveled is the area under this curve, we call this a curve just because we call all graphs curves in calculus, but it's really a straight line, right? So this is linear. So if we buy into that, okay, with time in seconds, the velocity of a bike in feet per second is given by this function, v of t equals 5t, then we should be able to answer this question, how far does the bicycle travel in the first 3 seconds after t equals 0? What do you think you might do? You do have all the information to answer that question. What's the shape, guys? What's the shape of that shaded region? What shape is it? Not a trick question, I promise.
Triangle?
Yeah, exactly. It's a triangle. And do you guys know the area for a triangle? You remember back from geometry? That was a long time ago. Yeah, 1/2 base times height. Thanks, Thomas. All right, so what we're going to do here is if you bought into the fact that the area under the curve, the original function, is going to be the distance traveled, then you should say, okay, well, all I need is the area of a triangle, which is just 1/2 base times height. All right, so let's see if we can pick out the base. What do you think the base is? You can read it, it's right on the graph.
Three.
Yeah, absolutely. Here's the base. And remember, this is 0, right? So how many units from 0 to 3? It's just 3. What's the height of the triangle? Again, it's right there on the graph.
15.
Yeah, definitely, right? Because here it is over here, right? This is a triangle. So this distance has to be the same as this distance, right? So we got 15. So easy peasy, right? 22.5 feet is the distance traveled. Now, obviously, this is not super realistic, but if they give you a linear function, then it's a triangle, right? Not very realistic because generally speaking, somebody doesn't, that's probably an average velocity, but there's a question like that. Any questions from you guys? Does that all make sense? Everybody cool? Groovy. Okay, now we did some rate of sales problems when we were doing the derivatives. So we're going to go backwards, right? So the rate of sales in games per week of a new video game is shown in the table. So just like in this prior example, where I'm showing you a rate, happens to be velocity in this example, I'm showing you a rate of sales, how many games per week were sold. It's kind of like how fast are you going, right? It's just another rate. And what I want to know is I want to know the total number of games sold during the period. Just like, I hope I'm not making y'all dizzy. Just like here, I was after the total distance the car traveled, right? Okay, so we're going to do the same thing. We're going to take a lower estimate. Oh, I probably need to step it away. And lower estimates, you're always worried about those numbers on the left, right? So the lower estimate would be the 0. And what's it measuring? Like, how often is it measuring the games per week? Like in weeks, how many weeks at a time are they measuring?
5 weeks.
Yeah, definitely. Thank you. 5 weeks. So the lower estimate would just be 0 times 5 plus what?
Plus 5 times 5.
Well, we're doing 0 times 5 seconds, then what's the next rate of sales after 0 that's listed?
Like 5 to 10. Is that what you mean?
No, I mean first our rate of sales is 0, right?
Mhm.
And that's after 5 seconds. Now the next rate listed is 585. But we're still at 5 seconds, right?
Okay.
Next. What else? What comes next?
892 times 5.
There we go. And then, let's see, let me backtrack there. Plus, let's see, after 892 comes 1875, still 5 seconds intervals, right? And if you add up all of those, you're going to get 16,760 games sold. That's a lower estimate. The upper estimate will be these numbers here, right? We don't take the first number. So what do you guys think? What are we going to do? What's the first rate that we're interested in? We know it's after 5 seconds.
The 585.
Yeah, very good. And then we go to the next one and so on, right? Oops. And as you would expect, these numbers are going to be bigger, right? Because the numbers get bigger each week. If you add all those up, you'll get 28,510. So if we have a lower estimate and an upper estimate, there is a better estimate. What should we do? We did it in the last problem.
Take the average.
Yeah, definitely. So we know that the game sold is in between the lower estimate of 16,760 and the upper estimate of 28,510. So if we take the average of those two numbers, it's a better estimate than just leaving the upper end and the very lower end. So here we could say, with the numbers we're given, this is kind of the best that we can do. And so watch on Wiley if they're asking you to estimate. Because I'm going to show you a formula for getting the exact answer, but if they're not asking you for the exact, they're asking you to do the lower estimate, the upper estimate, and then average the two. So this is a good estimate, and I should use this squiggly line to notice that it's an estimate. Games sold. Okay, let's look at another application. Let me wait a second. It looks like people are still writing. I want to write here. All right, everybody good? Okay. All right, here's another totally different example. So here it says, well, this is all about a bacteria population growing. Well, it makes sense that that's also another type of rate, right? So in this example, what they're doing is they're giving you the actual function. And this is exciting because, well, we probably won't do it until 5.2. Eventually, I can give you the formula and you'll be able to find out exactly what it is by putting the original function in. But if we don't have if all we're given is the original function, what they want us to do in this table is figure out what f of 0 is, what f of 2 is, what, just put those numbers into the function. But it's different for each, depending on what they're asking you for. So in this first one, they're asking you for change in t is equal to 4 hours. So if you think about total number of hours is 20, I'm getting that from up here. And you divide that by 4, right? Every 4 hours, you're going to get intervals of 5, which is the n value. 5 is n is intervals. So here, even though they're giving us 10 intervals in our table, the only thing that this question is asking you about is 5 intervals. So what we're gonna do is we're gonna fill in, if I did, and I'll show you, f of 0 equals 3 plus 0.1 times 0 squared. So if you put that in, obviously you just get 3, right? Because anything times 0 is 0. So that's where I'm getting that. We would do that same thing for every 4 hours. So the next interval would be at 4 hours, right? From 0 to 4 is 4 hours. So now we're interested in f of 4. And if you did f of 4, you're going to get 4.6. And then the next 4-hour interval would be at 8. So if you did f of 8, you're going to get 9.4. And so on, right? The next interval that you're interested in is 4 hours from 8 hours, which would be another 12 hours, right? So this, you're going to get 17.4, and then 16, you'll get 28.6, and 20, you'll get 43. All right, now another thing you need to pay attention here is if they're asking you for an upper or under, this is a lower estimate they're asking you about. So for all of these questions, and I mean, I have A, B, and C to ask you, all these questions, they're referring to an underestimate. So for an underestimate here, we're interested in these values, right? Okay, so if we did that, we would have well, let me get rid of this. There we go. All right, we would have the rate, which is the f of t, right? The rate of 3, that's our first value we come to, times the number of hours that have passed. So what are you going to multiply it by?
4.
Yeah, definitely. Thank you. And then what's the next f of t that we're interested in after 4? I mean, sorry, after 3. That's probably confusing you guys. What's the next thing in the table after 3 that we just filled in?
4.6.
Yep. But we're still interested in 4-hour timetable, right? So you just keep doing this, 4.6, then we've got the next rate we're interested in is 9.4. We're still interested in 4 hours. 17.4, still interested in 4 hours. And finally, plus 28.6, again, interested in 4 hours. So if you calculate that, you're going to get 252 million bacteria. And notice what the graph is going to look like there. Do you see why, looking at the graph, that that's an underestimation? Can somebody tell me why that's definitely an underestimation?
Is it because it doesn't include 43?
Well, absolutely, but I'm more interested in you being able to look at a graph like this and tell me, is this an overestimation or an underestimation? We know it's underestimation because of how we just calculated it, but what in the graph tells you that it's an underestimation? Where are the rectangles with respect to the function f of t?
They're below the line.
Exactly, yeah. And notice that these are the rectangles that you just calculated, right? 3 times 4, 4 times 6, and so on, right? You just calculated all of these. And because it's under the curve, you know that's an underestimation. If it were above the curve, it'd be an overestimation. But remember, the whole problem wants us to, they're asking us for an underestimation. Okay, at t equals 2 hours, that would mean that we would be more interested in, That means we'd be interested in the data every 2 hours. So if we did f of 2, we're just going to put 2 where you see the, oh, I don't see that. Yeah, the t value, you're just going to put a 2. If you did f of 2, you put 2 in, you'd get 3.4 out. So sometimes you have to calculate the rate yourself. Okay, so for 2 hours, probably can move this up, well, maybe not. So for 2 hours, we're going to take the original 20 hours. And this time we're going to divide it by every 2 hours. That's going to tell us how many intervals we have. So we get 10, that's number of intervals is always represented by a little n. So this is intervals. So we're still doing a lower estimation, right? But what rate are we going to start with? You guys think? Let me put so you can see the table. So see how in the 4 hour interval, we started with the 3, multiplied it by the 4, because we're talking about every 4 hours. This time, we're going to take something and multiply it by 2. What's the first thing we're going to take and multiply it by 2, do you think? Well, it's the same thing that we did up here, right? We're using this and this, these two rates, but we're going from 0 to 4, right? Now we're going from 0 to 2, and then 2 to 4, and then 4 to 6. So we're going to have more information here, right? So you'd start out with a 3, again, times 2, plus the next number, next rate that we have 2 hours later is 3.4 times 2. And then the next rate would be 4.6 times 2, right? Plus so on, so on, so on, until you get to the end, which would be 43. Where did I get that number? Let me make sure I filled this in right. Oh, I didn't fill them all in yet. Yeah, sorry. So 6, you would get 6.6. 10, you would get 13. And this is just putting f of 14 in, you would get 22.6. And for 18, you'd get 35.4. Okay, so you keep doing that, right, until you get to the end one, and the end one would be 35.4, again, times 2 seconds. So if you calculated all that, you'd end up with a different number. Is this number going to be bigger or smaller, do you think? Like if you did all this calculation, is it bigger than 252 million or smaller? Think about it this way, guys. This is definitely an underestimation, but so is this, right? But do you see how there's more room that we are not calculating in this graph? So this number is going to be smaller than this number is, right? Because more of the area is being taken up because the intervals have increased, right? So you would expect that this number would be bigger than this number because it has more intervals, right? So there's less area that's not being accounted for. Here, they've got bigger spots in between there, right? Okay, so this ends up being bigger, and you get something like 288 million. And this is still an underestimation. But if you guys bought into the original thing that if you keep making the interval smaller and smaller, the exact answer will be the exact area under the curve. So if you measure more often, you're going to get a better estimate, right? So really 288 million is a much better estimate than our original 252 estimate.
What formula are you using to find the numbers in the like bar graph?
Oh, let's go all the way back here. Oh, you mean to find these numbers?
Yep.
Oh, I'm just like, for example, to find f of 0, I'm just putting 0 in right here for t in this formula, right here.
So you've
So
been using that formula the whole time?
for this table, yes.
The f of t1, right?
Yeah, this is the only time that we have been filling in our own table. The examples before this, they gave us the numbers. Does that make sense? Awesome, thank you, Jack. Okay, and then here, they want to do the change in time. They want it equal to 1 hour. Now, I'm not going to list that table out. I didn't bother copying that. But you can imagine that compared to this estimate right here, what's going to happen when I make the intervals 20? Is it going to get bigger or smaller? Different question. Is the area of these rectangles more than or less than this? Okay, so there's something here that I'm not getting across here. Let's look at these two graphs again. This is an underestimation, so is this, right? So we know that the actual amount is all the area under the curve, including the parts here that the rectangles don't hit, right? So you see how the bigger spaces are in here? There's a whole bunch that's not being accounted for. If you look here, even though there's a lot of them, this amount right here is getting closer to the curve, right? So you would expect that this estimation is definitely underestimated, but this is a better estimation and it's going to increase because it's getting closer and closer to the curve, right? So if you calculated all the area here, it's going to be more area than if you calculated this area, right? Because these are getting closer to the actual curve. So it's going to go up. So if you go from 2 hours to 1 hour, you've got this time, and the table is not, table does not include this. I'm not right But I'm hoping that you would see that from 288 million, if you change the change in time to 1 hour, the intervals will increase and the area is going to get even more, right? It's going to go up. So let's pretend like we have the table and we did 20 divided by 1 hour. So you're going to get 20 intervals. That's your n value. If you calculated that, like we did here, right? And I didn't bother to do that, but if you calculated that, you should be able to tell me that, yeah, it would definitely increase because these rectangles are leaving less and less space. It's getting closer and closer to the curve. So this area would add up to more than this area, definitely. So it's getting closer, right? So as you would expect, yep, we get 307 million as opposed to 288 with only 10 intervals. Oops, what am I trying to write here? Okay, so let's make a note just to make sure you guys got the basic stuff you're supposed to get from this. This is what you're supposed to get from this. The smallest, let's see, note, the smallest change in T, and notice that if a change in T is 1 hour, right? And the largest number of, well, smallest change in T would equal larger intervals. I should say larger number of intervals. And this would give the best estimate. All right, how are we doing, guys? Everybody okay? Yep, I see some nodding. Cool. All right. This is the last page of 5.1. How are we doing on time? I should be able to get to what I want to in 5.2. Okay, so the graph on the left is what we call a left-hand sum. And the reason why it's called a left-hand sum is because of this. Each rectangle touches the curve on the left side. So at that picture, can you guys tell me, is that now it's still a left-hand sum, but is it an overestimate or a lower estimate or upper estimate, you think? Just by looking at the graph. Lower or upper? Is it more than the curve or less than the curve?
Upper.
Thank you. Yes, this is an upper estimate. Because the rectangles are above the curve, right? The one on the right side is an underestimate, or what do we call it? Lower. Right? But the one on the right is, notice that each rectangle touches the curve on the right edge here. So to figure out if something's a right-hand sum or a left-hand sum, you have to figure out, okay, where is the rectangle touching, on the left or the right? So here it's touching on the left side, right? And the one on the right is touching on the right side. Now, don't think that every left-hand sum is going to be an upper estimate, because it may not be. For example, sneak this drawing in here. Let's say I had a drawing something like this. And the graph went like this. And I still have the left edge touching. So that's still a left-hand sum, but it's an underestimation, right? Or it's a lower estimate. So whether it's lower or upper depends on if the rectangles are above or below, right? It's a left-hand sum if the rectangle touches the curve on the left edge. It's a right-hand sum if the rectangle touches the graph on the right edge. All right, now let's take a look at this. Did I have a bigger copy of this somewhere? Yeah, in the next section. We'll just give you a little overview here. This is this is SUMA, right? Yeah, right? Yeah, it's for sum. Okay, so basically what we did is we added up, if we're doing a left-hand sub here, from t is equal to 0, right? And we took the rate and multiplied it, this is the rate, and multiplied it by, like, let's say 2 seconds or 1 week or whatever we did in each of those examples. So this is the formula for a left-hand sum. And really, it's just saying what you did, right? Rate times the change in time. So sometimes we had a 4-hour change in time, sometimes we had a 2-hour change in time, right? But it's the same change in time, right? As you're just building the rectangles is all that's doing. On the right side here, if it's a right-hand sum, instead of starting at t of 0, we're going to start at t of 1, because if it's a right-hand sum, then the curve is going to touch at the right side. So these are formulas, and don't worry, you won't have to memorize those. You basically just did it. It's just showing you, summation means add all these things up, right? So they're saying add the first rate times the change in time by the second rate times the change in time, and so on. All right, now let's give you a graph example. So the figure here shows the velocity of an object from 0 to 8. It looks like hours, right? So both of these graphs show velocity from 0 to 8. And you're going to calculate the following estimates of the distance an object travels between those two intervals from 0 to 8. And then you're going to say, is this an upper or is this a lower estimate of the distance? Okay, so first thing we need to know is change in time. And how you calculate change of time is you're going to take your upper, subtract your lower, right? So the upper here would be 8 and your lower would be 0. And you're going to divide it by the number of intervals. So for this example, the whole example, both sides, we're going to say 8 minus 0 divided by 2 is equal to 4. So change in time is every 4 hours. Where do I obtain this too? Oh, sorry, they're asking different questions here. Okay, I get it. All right. Okay, so they want us to write it in this format, right? Here, they want us to write it in this format. And you'll see why we're doing that in a minute. Let me make this a little bigger. Okay, so the left sum, and I'm just using the formula from above, would look like n minus 1. And then we're going to start when t is 0. And then we're going to say f of t of whatever that time frame is, times, this is just a formula for you to follow, times the change in t. Okay, so if we look here, this rectangle is right there. And notice that, oh, that's the wrong graph, sorry, I'm drawing a left sun. Okay, so here's where the graph first touches at t is equal to 0, the graph. So the rectangle that you could draw there, and we know this is, okay, so let's get some numbers to associate with that. Okay, so there, the left-hand sum, this would be 6, right? The left side, 6 times, and our intervals end up being every 2 hours. And then we add the next left. So I would say that's somewhere, if you go over between 6 and 7, and you would say, okay, the next rate that we noticed left-hand side of the graph is at 7, and we're still measuring every 2 hours. And then the next one up here, I would say that that's going with 8 here, right? And 2. So we've got 2 and we've got 8 up here. This is 2 and this was 7. This was 2 and this is 6. And so on, right? So let's see, this looks like it's about 11, something like that. So first let's add 8 and 2. And it looks more like it's 11 than 10, right? Oh, no, it's right at 10. I just drew it wrong. Let's do it at 10. Plus 10 times 2. Add all those up and you get 56. And is this a lower or upper estimate, guys?
Lower.
Thank you. Okay. So notice too, one other thing I wanted to tell you here, that what we ended up with here is the change in T. So notice that there are 4 intervals. Right, that's where we're getting at. Same thing on the bottom one. Okay, so now let's do the right-hand sum with n is equal to 2 subdivisions. So we would say n on top, not n minus 1 here. I'm just referring to the formula itself. This time we're going to start with I is equal to 1, meaning the first interval. And the formula is going to be f times whatever the ti is we're talking about times the change in t. Okay, so this time we're going to start with remember, if it's a right sum, it's where it hits the graph on the right side. So let's draw those in. So if you draw it on the right side and then go directly over, this is going to be somewhere like 7, right? So we've got 7 by 2 plus, if you draw this over, it looks like 8 by 2. And the next one, you draw this over, it looks like it's a little more than 10. So let's say 11 times 2 plus 14 times 2. Because if you draw that right side, this is going to go over here to 14. So if we just draw the rectangles, notice that it goes above. Oops, that one should be here. Goes above the function line. So is this a lower estimate or lower upper estimate? Anybody? My question is this a lower or upper estimate? Is it an under or over estimate?
Upper.
Upper, definitely, right? Because it goes above. You can say this is an upper estimate. Okay. So now we're going to get to know a little bit more about the formula and how it's calculated. We've got 15 minutes. Let me look at 5.3. I think it would be better. To do 5.2 and 5.3 on Wednesday. Because they're both pretty short sections. So I'm going to leave with that because I want you guys to be able to do that work. So I would change the due date of 5.2 to, and I'll put it to the same due as same due date as 5.3. You guys don't have a lot of homework tonight, but if I were you, I would do it right away because it's so much easier once you've heard it. If you wait and go back, you're going to have to go back through your notes, and just since you just had it, you're going to go to the Wiley problems and they're just the same. And I'm even letting you out 15 minutes early. So I would highly recommend that you do it now because it's not complicated. But if you go back to it in a week, it's going to seem complicated. Everybody going to do that for me? All right, cool. You guys have an awesome day, and I'll see you on Wednesday. And if you have
Thank you.
any questions or concerns, just email me, okay?
Thank you.
or even text. me.
Thank you.
Thank you.
Thanks,
Thank
guys.
you.
Thank you.
Thanks, guys. Have a good day.